Chapter 5, Section 1 are conic sections. Yay! I hear the cheers going up. So when we talk about conic sections, we're talking about taking a cone and cutting a section out of the cone. And it's a cross section is what it is. So if I slice this cone at an angle to the axis from the vertex straight to the center of the base down here, I cut something at an angle, not parallel to the axis, but at an oblique angle, then I have what is called a parabola. Now, we've studied parabolas in the past. We're going to take a different approach to parabolas. It's still the same shape, but we're going to approach it from this conic section idea and learn a form of the equation that is useful for all the parts to a parabola, which are a little bit more than just vertex, axis of symmetry. Remember that from Algebra 2? We do have a vertex, and we do have an axis of symmetry, but we also have a point up here. I'll assume that that's the point right there. It's probably not. Called a focus. And so we are going to be real interested in that focus point as well. So here they give an illustration in your book, and what we are going to start with is the parabola right over here. Now there are 4 different conic sections in this chapter we will study. We start with the parabola, then we are going to go on to the circle, I think, and then the ellipse, and then the hyperbola. So those are the conic sections. So truthfully, we have 2 cones, and the parts to the cones, I only have one. These are called napes, N-A-P-E-S, napes. So there's a nape here, and there's a nape up there. All right. So what are the things that go with the conic section of the parabola that we will be interested in? Well, we will be interested in the vertex. We will be interested in this axis of symmetry that comes right down here. We will be interested in the focus that is right over here. And we will also be interested in a line called the directrix. Now, the definition of a parabola is, and the definition is going to be similar for all our conic sections, describes points in a plane, in a surface. A parabola is the set of all points in a plane whose distance from a point called a focus and a line called the directrix is equal. So let me pick this point, which happens to be on the parabola. If I measure the distance from that point to the focus and from that point to the directrix, it's the same length. And if I take any point on the parabola and measure those distances, it is the same length. And so if you drew out a shape that had that characteristic to it, you start with a point and a line, and then you make all the points that are equidistant from those two things, you get a parabola. That's the shape that happens. So if I go to the vertex right over here, well, I know this distance and this distance are the same. And we call, the letter we are going to use for that is going to be A. The distance between the vertex and the focus, we're going to call that length A. So when we're going to see an equation, we're going to see an A in it, and that's what we're referring to. Oh, I said the wrong letter. P. Sorry. We're going to call that P. And so the distance, notice 0, comma P right there. I should have figured that out. So the distance down here from the vertex to the directrix is negative P. It's just in the opposite direction. So this directrix line is the line y equals negative P. It's the opposite distance, same length. We can move these vertices around, but we will start with our vertex right on the origin. That's the one that they have right over here. So here's that definition that I read off a minute ago. Parabola is the set of points in a plane that are equidistant from a fixed line, the directrix, and a fixed point called the focus. And that point's not on the directrix, so don't pick a point on the line or you won't get a parabola out of it. So here's our first look at the equation for a parabola. X squared equals 4py. And that P is the distance between the vertex and the focus. That length right there. When we have an x squared one, it is going to be a parabola that either opens up or it opens down. It's going to be one of those two things. And how do I know whether it opens up or opens down? It depends on this value right here. Is that negative or positive? That p-value, if it's negative or positive. If it's a positive, it goes up. If it's negative, it goes down. Here they have drawn them both right down there, and they throw a whole bunch of funny things that make it look really, really complicated, but it's not at all. And I'll show you how it is not complicated at all in just a moment. What about parabolas that go sideways? Well, they are the y-squared ones. The y-squared ones go sideways. Now, you may be wondering, why do we have a y-squared and the axis of symmetry is along the x-axis? Usually we say because it's what the directrix is parallel to. A y-squared equals 4px is a parabola whose directrix is parallel to the y-axis. An x-squared equals 4py has a directrix parallel to the x-axis. However you can memorize it. So let's see how easy these things really are. Here's an equation of a parabola. I know it's a parabola because I have both x and y, and one of them is squared. Whether it's x squared or y squared doesn't matter. It just changes the direction it goes. I want to rearrange this so it's in the form x squared equals 4py. So how would I get rid of this negative 1/2 x? Multiply by negative 2. And then my x squared would be by itself. Negative 2y. Just rearrange that by multiplying it by negative 2. Now I know that this negative 2 must equal the 4p. So I can figure out what p is. If negative 2 equals the 4p, because that's the position it's in, then p must have a value of, divide by 4, negative 2 over 4 is negative 1/2. So what do I know so far? Since it's an x squared, I know it either opens up or it opens down. Since the p-value is negative, I know it opens down. My vertex is right here at the origin, and I go down 1/2, and I will arrive at the focus. I wish they wouldn't have made it so tiny. So this one is going to be a kind of wide one. My directrix, now I'm just going to do a little sketch for a moment. It's going to look something like this. They didn't ask us to graph it, so right now we won't go. Did they ask us? No, they didn't ask us to graph it. My directrix is the opposite direction of my focus, so I just need to go up 1/2 right here. This is where my directrix is going to be. It's the same p distance, this is the opposite way. Now that's a horizontal line, so if I wanted the equation of it, I would just say that's y equals 1/2. And I could get the ordered pair for that. I had to go 0 in the x and down 1/2, negative 1/2 in the y. What did they want to know? They said find the focus. Oh, the focus is at 0, negative 1/2. What's the directrix? Oh, the directrix is the line y equals positive 1/2. And we're done. These parabolas are pretty easy. What is that just you wait statement? Let's try this one. Find the equation. Now these are standard forms that we've been working at, so they want it in the form that we saw. Of a parabola, it says the vertex is at the origin, and I like pictures. Vertex is at the origin. The focus is negative 2, 0. Focus is negative 2, 0. So my focus is here, my vertex is right there. Well, I know this thing is opening left, don't I? Because that focus is inside it. I know even before I get to the equation, I know my p distance had to go back 2. The other one we had to go down 1/2. It was negative. Well, this is left 2. Now, since is it a y squared or an x squared one? It's a y squared one. It's a y squared equals 4px. And really, all I need to know to write the equation is, what's the p-value? P-value is negative 2. What's 4 times negative 2? Negative 8. So y squared equals negative 8x. There's the equation of that parabola. They just wanted the equation this time. If I wanted the directrix, it would be 2 to the right, which is a vertical line, x equals 2. That's the equation of the directrix. I think if you draw pictures on these, it makes these, truthfully, pretty easy. I hope. Now, we get tired of the vertex being at the origin, don't we? So we're going to slide it around. But it's really, really easy. Let me write x squared equals 4py again. Do you notice that that is the same thing? The only difference is we have moved it right h, and we have moved it down k. So let's try to, and this is an x squared one, x minus h squared. It's an x squared one, so this is an up and down one. We just moved the vertex, is all we've done. P is still P. How we find the directrix is still the same way. This is just a y squared equals 4px1. We've just moved it. We just moved the x and y stuff. So let's try one of those.
H always goes with x and k always goes with y.
Yes. So what they are saying here is the vertex is the ordered pair h comma k. It can be any letter. So really all I care about is I look at the x variable, where the x variable is, and that's the x part of the vertex. And wherever the y is the y part of the vertex. So here's the x part of the vertex, there's the y part of the vertex. Let's try one of these fancy ones. Find the equation. Oh, well, they don't want the equation. Oh, they do want the equation, probably. Find the equation of the directrix, coordinates of the vertex, and the focus. I guess they don't want the equation. That is given by this equation. Now they're meddling, aren't they? What we want to do is get it into this form, and as I look at it, I say, hey, that's a y squared one. I want to get it into the form y minus k squared equals 4px minus h. Well, the way I get it into this form is I have to complete the square in order to get a perfect square trinomial, so I can make that little y minus k squared. That's the process. So let's go about that. Let me get the y's together on the left side. 2y squared plus 8y. Then I'm going to move everything else to the right side. So I'm going to subtract my 3x, and I'm going to add my 4. Negative 3x, and add my 4. Now, in order for me to complete the square over here on this y squared part, I need to factor out the 2, because I have to have unity, 1 y squared. So I'm going to factor out the 2. Y squared plus 4y. I'm going to leave some room to complete the square in there. Equals negative 3x plus 4. Now I'm going to complete the square on this part. Do you remember what to do to get the number, what we do with that 4? Divided by 2 and square it. So half of 4 is 2, 2 squared is 4. I'm going to add 4. Now I have to keep it balanced. Yeah, well, let's see. The 2 on the outside needs to be multiplied by that 4 that I just put there, so the value I added was 8. If I was sticking on the same side, I would then also subtract 8 to keep it balanced. But since I'm going to the other side, I'll add 8 over there. If I added 8 to the left side, let's add 8 to the right side. It's all balanced. So now this is a perfect square trinomial. 2 parentheses something squared. Y, and then is half of that plus 4. Y plus 2 quantity squared. Equals negative 3x plus 12. Now, I'm almost ready to divide by 2, but to make it a little easier, I am going to come back up here and notice that I just want one x here, x minus h. I don't want any number like a negative 3 out there. I'm going to factor out a negative 3, x plus 4, and the reason I did it that way is because now, when I divide by 2 to get rid of this 2, I can just put my 2 right there.
Wouldn't it be minus 4 because you factored out a
Did I? Minus 4. Thank you. Negative times a negative makes my positive. All right. Now I'm going to divide by that too. I didn't do it earlier simply because you can. Negative 3x plus 12. If I divide by 2 at this point, I get negative 3 over 2x plus 6. Now I need to factor out a negative 3 over 2. And maybe you're real comfortable doing that, but I have to divide out that negative 3 over 2 from the 6 as well, which you can do. It's just a little easier for me to, let's go ahead and factor it while it's easy, and then I can divide by 2. There we are. We've got it in the form that we need. I know where my vertex is. I go to my x's, it's at 4, it's always the opposite, minus 2. That's where my vertex is. Now I need to figure out my p distance. That's the next key, so I can get everything else. And I realize that whatever this number is what 4p equals. 4p equals negative 3 over 2. So I'm going to get rid of that 4 by multiplying by its reciprocal, since I have a fraction that makes it easier. P must equal negative 3/8. I'm going to use a picture to help me out. Before I try to answer anything, 4, negative 2, write 4 down 2, there's my vertex. Now it is a y squared one, and the p is negative. Can you tell me which direction it opens? Goes to the left. I need to go to the left 3/8. Now that's not very far. Right about there. There's my focus. My parabola is going to be going this direction. 3/8 the other way is going to take me to that directrix. So I just need to figure out what those points are. That vertex, remember, was 4, negative 2. I backed up 3/8 to get to this focus. So 4 minus 3/8. You can do a mixed number if you want. 3 and 5/8. 8 times 3 is 24, plus 5 is 29/8. Now, to me, it was easy to do with mixed numbers. I'm subtracting 3/8 from 4. Well, I'm back to 1 less, 3. And what do I have left over if I've taken 3/8 away? 5/8. 3/8 and 5/8 makes 8/8. 1. Whatever is easy for you. 29/8. That is the distance I am at. 3 and 5/8, negative 2. My focus is 29/8, negative 2. And really it's just working with the fractions that make it complicated in any way. So that's why that makes it college algebra, because we have to be a little complicated. Now I need to go 3/8 to the right to get to this line. I was at 4. If you add 3/8 to 4, where are you? Do it the easy way, the mixed number. You're at 4 and 3/8, right? So if I am at 4 and 3/8, 8 times 4 is 32, plus 3 more is, I'm at 35/8. And it's a vertical line, so it's x equals 35/8. X equals 35/8. What did they want? They wanted the vertex, we got it. They wanted the focus, we got it. They wanted the directrix, we got it. When they make them integers, really, really easy. I just went over 1, I went back 2. When they do fractions, you just have to be careful, do the same idea. You're adding or subtracting that p distance. If it's a fraction, you'll just get a fractional answer. What else can they throw at us? Find the equation in standard form. So we want the equation of a parabola. It has a directrix at x equals negative 1. Well, that's a vertical line. There's my directrix. Right away, I know it opens just with that, either to the right or to the left. So what is squared, the x or the y? The y is squared. You're right. I had to think a minute. The y is squared, parallel to the y. What do we have? A focus at 3, 2. 3 comma 2 here is the focus. Where is the vertex compared to where the directrix and the focus? Right in the middle. What's the distance between these two things? Can you just count them? 4. So right there is the vertex. And how far do you have to go to get to that focus? 2. That's called the p-value. In fact, we had to go to the right, so it's a positive p-value of 2. Now my vertex, what are the ordered pairs? We can just tell from the graph. 1 comma 2. 1 comma 2. And we already established the fact that it was a y squared one. So I'm going to be filling in y minus k quantity squared equals 4p x minus h. We're going to be filling that in. Y, what was our k value? 2, positive 2. So it's y minus 2, quantity squared. 4 times p, what's p? 2. What's 4 times 2? 8. X minus 1. That's a 1. X minus 1. There's the equation of that parabola. And I go off the diagram. I go off the picture. So why do we care about parabolas? Because of their reflective properties. And that focus that we have been talking about is literally where things get focused at or concentrated at. If you have a parabolic shape, anything that comes in parallel to the axis, here's the axis, so you just point that axis at something that's coming in this way, it will bounce off your parabola and be hit right on the focus. So here you have this thing called a satellite dish. And those radio wave signals come in and they bounce off and they all get concentrated right there. And the reason we want them concentrated right there is because one little signal is not strong enough to pick up with our receiver. So we get a big dish, so it gets a whole bunch of those little signals and it sticks them all in the same spot, so it's big enough for us to pick up. You can do that with satellite dish. You can do that with sound. Have you ever seen on the sides of sporting, sometimes watching on TV, there's this guy that's holding this kind of glass-like looking parabola. It's got a microphone right at the focal point, the focus, the focal point. So you can hear light sounds. They all bounce off and hit in the same spot and gets concentrated in that point. So you get yourself one of those parabolas and you hook it up to a headphone and then you aim it across the campus at that window where that person that you're really interested in is, and they're talking and that window vibrates a little and it amplifies it in your nice parabolic receiver. And they listen to you in their little van parked out there on the street in the dark. I mean, you've seen that. All right. So what else do? We do the opposite thing with them. A headlight or a flashlight has the light bulb at the focal point. So when the light spreads out in all directions, well, it hits the parabolic surface. Now, these things are called paraboloids, not just two-dimensional. They're rotated, three-dimensional. They become three-dimensional objects like this. If I take two lines and I rotate them in space, guess what I get? A cone. I get this thing right here. I have two lines that I've just rotated in space. I get a cone. So that becomes a paraboloid. You have had flashlights where you could turn them and the beam goes like this. It's sliding that light bulb. When it's right at the focus, you get a parallel beam, a spot. And when you move it out or in, then it changes. The shape of that beam is what's going on. Different type of telescopes can also have a parabolic reflecting mirror, so it focuses everything back over here. All right. So let's try it out. A satellite dish has the shape of a paraboloid. The signals that it receives are reflected to a receiver located at the focus of the paraboloid. If the dish is 8 feet across at the opening and it is 1.25 feet deep at its center, determine the location of its focus. So we've got one of these things going on. Well, we can draw it however we want. So I am going to draw it with the vertex right at the origin. And then I'm going to go ahead and draw this thing as an x squared or y squared? An x squared. So I'm going to see if I can figure out x squared equals 4py. Now they gave me some hints. The depth of this, they said, if I measured across, was 1.25. 1.25. Now they did not say that the focus was right at that depth. They just said that's where the paraboloid stopped, at that depth. And it was 8 feet, all the way across was 8 feet. I want you to tell me the coordinates of that point right there on the end of the edge. 4, 1.25. 4, 1.25. Now that happens to be an x and a y value, is that correct? I bet if I substituted those 2 points into my equation, I could solve for what the p-value was. And if I know the p-value, I know how far I go to get to where the focus is. And they wanted to know, where is the focus? Well, we're going to figure it out. X is 4. 4 squared equals 4 times p times our y, 1.25. What's 4 times 1.25? 5. Good answer. What's 4 squared? 16. Divide by 5. Was this measured in feet? What's 16 divided by 5? 3.2. 3.2 feet above the center of it. So what do? I get my nice measuring stick out and I measure 3.2 feet, and that's where I put the receiver because it's right at the focal point, and all my rays are focused right in that spot. Those are parabolas. We're done. I'm done.